the recording? Okay, great. Okay. Thank you. You're fantastic. Appreciate it so much. Just add it to the stack because I have so many worksheets. Okay. We're actually going to get started. Thank you. Hey, friends. Hey. I do apologize for taking so long to get started, but as you see, my life is crumbling. So, you know, it's fine. Everything's fine. Okay, so we're going to practice some specific heat stuff to refresh our memory from Tuesday. And then we're going to go into applied specific heat stuff so that we can use this to help figure out information about other stuff via calorimetry. So let's review. All right, we've got two formulas that we were working with. Q equals MCAT and Q equals M delta H, or meh, which is how I feel. So we're going to be working pretty much just with the specific heat formula today, but just a refresher, what does the Q stand for in both of these? Amount of what? What do we call it? It's not just energy. We call it, the word is on the board right now. Heat. It is thermal energy. So it is energy, just specifically thermal energy or heat. All right, so that's for both. What is M? Mass. All right, what is C? Specific heat. The number of times that I see people get those two things mixed up, heat and specific heat, please make sure you have those letters straight in your head. And then what does the triangle mean in this situation? Means change. So delta T is change in temperature. All right. And then over here, the only different letter is my delta H. It's not change. It's part of the H. I don't know, man. I didn't make the rules. What does that mean? It does involve the word heat, but not heat change. Heat of something. You have two options for this. It's either fusion or vaporization. If it's heat of fusion, this is when we're talking about melting or freezing. If it's vaporization, we're talking about boiling / evaporating or condensing, right? So we got two options. We pick according to what phase change it is. What thing do we not have in that second formula? That is present in the other one. What doesn't happen at a phase change? Do we remember the graph? Okay, no temperature change. There is no temperature change during your phase change. All right, so even if you're given a temperature in a question, don't you dare use it. Because I can be given a temperature when I'm talking about like what ice melts at 0 degrees. That 0 is not actually helpful if I'm asking how much energy does it take to melt the ice. Because I'm not changing temperature. It's all happening at 0, right? Okay, so there's the formulas. The one we're going to be focusing on is the specific heat formula, so the one on the left. Excuse me. All right, so we got All right. What is the specific heat of a substance? What am I solving for? Specific heat, which is what letter? So that is my X, my unknown. All right. That absorbs 2.5 times 10 to the third joules of heat. That is what letter? Somebody else answer me. I love that you know, but you can't be the only one in this class that knows. So, all right. When a sample of 1.0 times 10 to the fourth grams of the substance, what letter is that? M. Increases in temperature from 10 degrees to 70 degrees. What number do I put for delta T? I'm hearing so many numbers. All right, I'm hearing 60 or negative 60. It's not negative 60. It's going to be 60. And how did you get that, Jocelyn? Right. So anytime you're calculating delta T, do your final temperature minus your initial temperature. So in this case, 70 minus 10, that gives us 60 degrees. All right, the question asks us to solve for C, so let's rearrange our equation before we actually put any numbers in, because that's a lot of writing otherwise. All right, how do I isolate C here? What math do I do? You're good. Divide by M delta T, the things that I'm trying to get rid of, right? So that will cancel those guys. And I'm left with C equals Q over M delta T. So, bless you. So we just plug it in. All right, so Q over M times delta T. All right, just a refresher, because it's been a while since we've consistently used scientific notation. When you're typing it in your calculator, if you have that EE button, you type the base, and then the E, and then the exponent. I know it's tempting to put the 10 in there. No. No, no. Do not put the 10 in there. Just base, E, exponent. All right. If you don't have that button, or you have a calculator like my, bless you, my smaller one, if you've ever borrowed my small calculator, you're just going to have to put it in parentheses in order to make it work. Because, you know, order of operations and whatnot. That's particularly important here. If you're typing it all in at once, the whole bottom needs to go into a set of parentheses. And a cool kid named me did not bring the answer key to this one. Yay. That's not right. Oh my God. That's not right either. Well, maybe it is. What'd you get? What? Yeah. All right. You should have gotten a really small number for this. C equals 0.004. Hey guys. I'm struggling to think in silence. I definitely can't think with all the side conversations happening. Remember that whatever math you do to your numbers, you are also doing them to your units, which is why if you recall from the other day, our specific heat is measured in joules per gram degree Celsius because it's joules divided by grams times degree Celsius. So did you, if you don't use parentheses for the bottom, then what you get is this divided by this, and then whatever the answer is times 60, which is not what you want. Is that what you did? For the whole bottom altogether? I don't know. I would have to see what you typed in. Okay, you have to put the whole thing in one parenthesis. So hold on, delete, delete. So it should look like this. Okay. Yeah, because, and I don't know if this is the case for your calculator, but if you put, like I put parentheses next to each other like that, most calculators don't know that this means multiply. We do. Some calculators you have to explicitly state it. However, in the case of how you typed it in, all right, guys, pay attention because this is, a lot of people type it in this way. And in this case, multiplication and division are interchangeable for PEMDAS, right? So you've got 2.5 times 10 to the third divided by 1.0 times 10 to the fourth times 60. If you do it like this, rather than putting the whole bottom in parentheses, whether your calculator recognizes two parentheses next to each other or as multiplication or not, if you don't do the entire bottom in parentheses, then multiplication and division are interchangeable, and it's just going to read left to right. So it's going to say this divided by this, and then the next math is going to be times 60. So you have to have that entire bottom chunk in a set of parentheses if you want that times 60 to be the bottom of your fraction that you had. Does that make sense? So, shoop. All right, let's look at the next one. How many grams of water would require 2.20 times 10 to the fourth joules of heat to raise its temperature from 34 degrees to 100? The specific heat of water is 4.18 times, or 4.18 joules per gram degree Celsius. So, what formula are we using? Why do you know that? Okay, if you read the question though, how would you know based on the question that it's Q equals MC delta T rather than Q equals M delta H? Okay, so if you know specific heat, right? Sure. What else in here tells us? A temperature change. So we're raising its temperature from this to this. So whether you zero in on the word raise or the fact that I am going from one temperature to another, either way, that's a change in temperature. Okay, so what variables am I given? And I'm just going to call on people now because I'm mean. Wyatt, give me one of the variables that is given to you in the problem. Yeah, 2.20 times 10 to the fourth. Excellent. All right, let's see. Dylan, hey friend, give me another variable that's given to us in this problem. We already have Q. What else do we know? Excellent. Oh, why do I keep trying to write times? Okay. And then Armand, what's my last variable that we are given? Delta T. So how do I calculate it? Because it's not given to me as delta T. 100 minus 34. So 66 degrees. No, we don't do Kelvin. It actually doesn't matter though, because a Kelvin and a degree Celsius are the same thing size-wise. So this could be joules per gram Kelvin or joules per gram degree Celsius, and that specific heat would not change.
So we can write K
If you want, to convert it, sure, but even if you convert it, it's still changing by 66 Kelvin because they're the same size of a unit. So I would not waste my time personally. It's just like one extra thing, and one extra thing that you could easily screw up if you type it in wrong, or you're like,
It's like an extra step that could mess up.
yes, correct. You're welcome to. You'll get the same answer, but I wouldn't. All right, so we're solving for M. How do I get to M by itself? Divide by cat. It looks like an A. It's just so much funner to think of it as Q equals MCAT. And then for those of you who are potentially thinking about maybe one day going to medical school, you have to take the MCAT. Look at that. Reminds you of your goals every time you do it. All right, so Q divided by C delta T. So again, cool kid didn't bring her answer key. Brought the answer key to all the other worksheets I brought, just not this one. Gareth, do you have an answer? Oh, you and your rounding. Yes. 80 grams, or as my calculator said, 79.74481,659. My brain does not want to think about that. You said 80 and I'm immediately like, no. No, it's 80. 80 is fine. 80 is totally fine. My brain is just not processing. Okay. I am gonna skip down to number 4. Yeah, hi. I generally don't care. 80 is normally fine. Today, on the day that my brain is not working, 80 was not fine for a minute until I processed. I should care because, significant figures and all that. I really don't. If you put 79.7448, if you put 79.7, whatever. All right, so I'm going to look at number 4 now. All right, a block of aluminum weighing 140 grams is cooled from 94.8 to 62.2 with the release of 1,080 joules of heat. From this data, calculate the specific heat of aluminum. So what formula are we using based on the word problem? The same one. How do you know based on the word problem? The temperature is changing. Yeah. Who is saying? Stop it.
It's not us.
You guys, cut it out. Okay. What do we know? Ella, tell me a variable that you know based on the word problem. 140 grams is M. Fantastic. Tristan, hi friend. Give me a variable that you know from number 4. And what letter does that go with? Okay, it does. However, it's not wrong. But this confuses people, and it doesn't affect your math. However, the number of times that I'm like, what if I get a negative number? Like that's the question I get asked a lot. So if we lose heat, or our change in temperature is that our temperature is decreasing, Q is going to be negative because it's losing it. Just like if you spend money, the dollar amount is going to be negative because you're decreasing by that amount, right? And the other piece of the question that has to be negative as well is delta T. So if you do final temperature minus initial temperature, this problem, you will get a negative number because it's 62.2 minus 98.4. So if you remember that both of these things are going to be negative, so it says it releases 1080, so 1080, right? If you remember that both of those pieces are going to be negative, your specific heat will not come out as a negative number, and all is well. If you don't remember that release of heat means negative, then you'll do your math, you'll get a negative for your C, and you'll ask me, what if I get a negative number for C? You just drop the negative off. It doesn't change your math. You need to understand that and think about it common sense wise, right? If I put a pot of water on the stove and I turn the stove on, am I adding heat to the water or taking heat away from it? I am adding heat, so my Q will be positive, right? So the opposite of boiling water, let's say I put that same pot of water in the freezer, I'm taking heat out of the water, so the Q would be negative, right? I'm not heating it up, I'm doing the opposite. So if heating up is adding heat to it, then the opposite is taking heat away. Uh-huh. Mm-hmm. Well, and the fact that my temperature is going to be negative if I math it out. It will have to be if you're releasing energy. Yeah, if you release energy, your temperature change will be negative because your temperature is decreasing. Okay. Did you get the right numbers? Okay, well then see? Doesn't matter. All right. So my temperature is negative 36.2 because remember it's final minus initial. So when I plug this in, and I'm just gonna, that arranges to C equals, not M, Q over M delta T. Bless you. Smooth. All right. Well, it's way over there. No chance. Go gadget leg. You'd have to be 10 feet tall. This is so normal right now. So normal. Okay. So if I do this math, I'm going to get a positive number, which is what I want. Your C is going to be positive. So I get 0.213 joules per gram degree Celsius. All I'm saying is, if you did not read this and go, hey, my Q is negative, then what'll happen is you'll do the math and you'll get negative 0.213. You will never have a C value. You will never have a negative mass value. So just don't panic. Just drop the negative off. That's the only reason I'm having this conversation with you. Don't panic. If you get a negative, that just means that you forgot to do this, and then now we're all good. then technically 62 minus 98 is exactly what I did to get negative. Okay, so technically that is doing the math as if it was the top form. It was the top folder. Hold on, just the top one. I've not handed out anything else yet because I don't know how much we're gonna get to today. So I just brought everything. Technically, that would be doing math as if you were increasing the temperature and not decreasing it. It matters in terms of energy flow. Mathematically, it doesn't. Just drop the negative if you get one. Just drop the negative if you get one. All right. So your C will never be a negative number. Your M will never be a negative number. So if you're solving for one of those and you get a negative, just drop it, because math, like number wise, it should be the same number, just negative versus positive. Okay. Question number 5. This one's a little tricksy. All right. A cube of gold weighing 192.4 grams is heated from 30 degrees Celsius to some higher temperature with the absorption of 226 joules of heat. The specific heat of gold is 0.030 joules per gram degree Celsius. What was the final temperature of the gold? So I'm changing the temperature, so we're going to Q equals MC delta T. All right, what pieces am I given? Shania, what's one thing that I know from the word problem number 5? I know my M, which is, correct. All right, Layla, what's one other thing that I know from the word problem in question number 5? I know C, and then what is that number? That's not C. Yeah. Definitely just tried to write that next to Q, but it's fine. All right. And what else do I know? Who can I pick on? John. What else do I know? What is Q? 226. Yeah. Okay. So I'm solving for delta T. So per usual, we will rearrange to delta T is equal to Q over MC. Anybody have that number? Okay, so now the important question. Are we done? Why are we not done? Somebody that I've not heard from. It's heated from 30 degrees Celsius, so what do I do? Add 30 to this? Yeah, because this is telling you that I'm going from 30 to question mark, and now we know how much it changes when we do that. Right? So it goes from 30, increases by basically 40. So my final temperature is 69.15. Or 69 if you didn't give me the decimals or whatever. As I told Shania, I'm sure I should be more concerned about number of digits, but I'm not. So. Okay, I'm going to give you guys a few minutes to do question number 6 and 7.
Did you just say? Wait, what question?
Number 7 and 8. Dang it. I hate you all. No. Please no. Listen, I'm going to have like 200 middle schoolers here on Saturday. The number of times that I'm going to hear it, I'm sure is insane. So please no. Please no. 7 and 8. Yeah, I changed it. You are welcome to do number 6. However, I will not be addressing that question anymore. All right, so take 7 minutes because I like weird numbers. Take 7 minutes, ask me questions where you have them. No, I do not have an answer key, so I can only look at your work. I can't tell you 3 answers right. Shemaya, we're just doing the same math we were doing on Tuesday. We're just recapping before we apply it to something. So, yeah, the same Q equals MC delta formula. And actually, it's a good thing you didn't actually take these because the next thing I'm going to give is actually done really well. Because we're going to apply it. I don't know. It's not me grabbing like 3 of them when I need to hand them out to everybody. It's right. Not that one. Oh, yeah. No, it had the graph on the front. Oh, okay. What's the graph? Yes. This 10 minus 10. Graph. That. Lock in. Yes. Are you here today? Well, that'll do it. You don't have it. If you weren't here Tuesday, you don't have it. So almost. That means you're only going half crazy, I think. I think that's Yes, I did. I have it written down on a pen. Damn, I know you did on the stage. Where? You know what? It's a time like this that they can code it. For when your brain. I do. Wait, oh. 10 minus negative 30. Yeah. Okay, that's all I do. Stop it. It's not what it's supposed to be. It's not 35. What the heck? Good Lord. You guys. Oh my God. When in doubt, calculator it out. Please. I saw the people over here first, so I'm gonna have to go over there. I know you are not. Also, I have to there. Actually, except 9 is
Make sure when you're typing that you do not miss the one that's from that means you're gonna have more training. So you're having me size very small. Probably, is it just on this, or are we going? Anyways, this, we're not going from. To where you'll remember it, can't promise that. We spent all class last period, last month talking about it, and all class today. I would suggest that you figure out a time for office hours, because it's gonna take longer than the minute and 16 seconds that I have left on my timer to explain it. That's not office hours, though. Which are two different things. Because I'm not gonna be explaining this to you while you're taking a right? Okay. Maybe we can talk after you finish. And I'm also gonna stand up there and work through these two problems. So this is pretty straightforward if you know what the formula is, and you have to be able to pull the numbers out of the word formula. So. Yeah, because you're doing here. Okay, but the thing, hey friends, what is this? What is happening? No, because you're talking about 5 pounds of something. By 200 degrees. It should happen. So that's how much. So it actually gives you instead of giving you final addition. Okay, and then right. Yeah, make it quick. Walking out of the house and I cannot find it. They're rocks. I don't know a lot of shit.
No. All right, peeps. Let's go over. Okay, so for my friends that are new to the group, the formula we're using is Q equals MC delta T. Q is my heat, so how much energy is involved. M is mass. Delta T, the whole triangle T business, is change in temperature. So T final minus T initial. And then C, we call that the specific heat. So it's the amount of energy that it takes to change 1 gram of that substance by 1 degree Celsius. And it is specific to the substance we're talking about, which is probably why they call it specific heat. Okay, so sorry, I know you guys were all here for that, but I had some latecomers, so we had to review again. So now we are just pulling our variables out of the word problem. So Quentin, give me one variable you know in number 7. Yep. All right. Abby, give me a variable that you know out of this question. Yep. And then Blessing, what's the other one that we know? I know the change in temperature. Remember, it's final minus initial. So your change in temperature should be 25 degrees Celsius. Remember, minus a negative is the same as adding a positive. All right, this one, I'm solving for Q, so I don't have to rearrange my equation. I just plug it in like it is. So 550 grams times 2.03. Why am I doing times? Joules per gram degree Celsius. My brain does not want to do a specific heat correctly today. And then 25 degrees Celsius. $27,912.5. Do we have a winner? Did you get it? Is that what you got? Yes. All right. And then the next one. What do we know? No. Rashaya, what is one variable that you know out of question number 8? Delta T is 200 because I'm going from 0 to 200. Desmaya, what you got? What is our mass? 2.25 kilograms. And then what's the last thing that I know? Ashley. C, which is? You do. Because this guy right here is grams. If that was kilograms, then you could leave it, but it's not. So because that's grams, we got to convert. So times 1,000 to convert. So 2250 grams. Get 2250. And then 200. I have no idea what that number is, but it's big. $58,050 joules. All right. Some of these questions you're going to get really big numbers, and that's okay. Don't let the big numbers psych you out. In this case, if you just think about it, it should be a big number. You're taking almost 5 pounds of silver and raising it by 200 degrees. That ought to be a big number, right? Even if silver has a tiny specific heat, which it does, it still should be a big number because I'm changing the temperature of a whole lot of stuff. So don't let big numbers psych you out. Okay, so we're going to shift gears to that worksheet that I just handed out, which is on calorimetry. So this is the same equation, but this is how we would use it in a lab setting. Smooth move. You got some crumbs to pick up. Goody. Mm-hmm. Mm-hmm. Uh-huh. All right. So an 85.2 gram copper bar was heated to 221.32 degrees Celsius and placed in a coffee cup calorimeter. We will be using a coffee cup calorimeter in lab 28, which is the next to last lab of the semester. And you're going to have to do something like this on the final exam for lab. So let's do it. All right, so basically we have this copper and we heat it up to 221.32 degrees. A coffee cup calorimeter is made up of exactly what it sounds like, styrofoam coffee cups. All right, so we have this, and we always double stack them because it's insulated a little better when we do that. But the idea is a calorimeter is supposed to isolate whatever process you have going to the water and the space inside of the calorimeter. A coffee cup calorimeter is an easy way to do it for like lab purposes for us. There is also a thing called a bomb calorimeter where it's not as scary as it sounds. I don't actually know why they call it a bomb calorimeter, but this creates a sealed container that you pump oxygen into, and then you perform a combustion reaction. And so you can measure, this is how they figure out like the number, they can figure out the number of calories in a specific amount, like a specific piece of food or something, is through calorimetry. But the idea is we have this thing that's happening and we have water, and the thing may be difficult to measure, but the water we can measure very precisely. So in the coffee cup calorimeter, we know that we have 425.0 milliliters of water, and it starts off at 22.55 degrees Celsius. Water's density, if you don't know this already, I need you to go ahead and put it in your brain that 1 milliliter of water is 1 gram of water. That is important because the assumption is that you know this in order to be able to calculate this. All right, so when you see 425 milliliters, just go ahead and think 425 grams. All right, now I want you guys to think about this. If I do this, I take this very hot copper and drop it into my coffee cup calorimeter. What's going to happen inside of that coffee cup? It's definitely not going to boil. However, we are going to increase the temperature. It's water. It takes a lot of energy to boil it. That's not enough energy to boil it. But it'll increase in temperature. So what we know will happen is that this will increase in temperature. What's going to happen to the copper? It's going to cool down. To what temperature? Don't read the word problem. I'm talking conceptually right now. To what temperature? How do we know when it stops? when they are equal in temperature. So this guy is going to cool down. This guy is going to heat up until we reach what we call thermal equilibrium, where both things are the same temperature. So for lab purposes, this is going to look like you're going to be measuring the temperature like every 15 seconds. When the temperature stops changing, that's when you know you've reached thermal equilibrium. Right? So all right, and in this case, the final temperature of the water was recorded to be 26.15. Whoops. So final temperature is 26.15. Therefore, what do we know about the copper? I just said it, you guys. Yeah, the final temperature is 26.15. All right. So in a coffee cup calorimeter, you know that I'm telling you, you don't know, you're about to know. The amount of energy lost by whatever it is, in this case, it's a hot substance, is equal to, well, I'm going to put a negative on there, but is equal to the amount of energy. Oh my God. Heat energy. Look, man, brain not working. Heat energy gained by the water. And I'm actually going to erase that. But so that means Q for my copper is equal to, God dang it, I can't write today. Q for my water. So I know all of the pieces that I need to know at this point, right? Because I can calculate Q for my water. And this is kind of the steps for this ABCD are guiding us through the question, right? How much heat was gained by the water? Well, I can calculate that because I have my mass. I have my final and initial temperatures, so I can get my delta T. And what do we know about water specific heat? We've used it a lot. It's 4.18. All right, so Q for my water is equal to, remember, Q equals MC delta T. So 425 grams, 4.18 joules per gram degree Celsius. And final minus initial, so that's 26.15 final temperature minus the 22.55 initial temperature. My brain is not doing the things it's supposed to do. I'm not typing the right numbers. I'm not saying the right words. This is so annoying. So 3.6. So my water increases in temperature by 3.6 degrees. You see why I didn't boil it? It hardly changed the temperature at all. But so Q of my water is 6395.4 joules. And what do I know about that number? What is it also equal to? The heat lost by the copper. So all right. So now, question B, how much heat was lost by the copper? It's the same number. It's the same number. This is how we can do it because equilibrium is reached, where the temperature is the same. And it's because heat was exchanged. That's why we have to insulate it, with the double styrofoam cup or with the bomb calorimeter that's actually sealed inside of a vacuum sealed container. This is why, because we isolated it in something that is insulated, we can assume that none of our heat is being lost to the outside, right? If I did this in a glass cup, some of the heat would be lost to the glass and would go elsewhere. But because I'm doing it in a styrofoam insulated cup, I'm not losing heat to the environment. And because I'm not losing heat, I can make this assumption that we have made right here. That is tiny. Please hold. We can make that assumption. So now I have Q for my copper. I have the mass of my copper, and I can figure out the delta T of my copper. So now I can answer question C. What is its specific heat? So and remember, heat was lost, so that's a negative. M was 85.2. And delta T is whatever 26.15 minus 221.32 is. I don't have that number. That's a lie. I have that number. No, I don't have that number. I wrote it just like that. Okay. So the specific heat for my copper is 0.385. I'm telling you right now that on the final lab practical, you are going to have to identify a piece of metal, like what substance it is, based on a coffee cup calorimeter. So you're going to physically do this. In lab 28, we practice using a coffee cup calorimeter. In that lab, we do it with a reaction and not a hot thing that's cooling down, but it's the same math that we're doing. So you're going to have practice in lab 28, but you're going to have to do this exact thing and then figure out, okay, specific heat is 0.385. What substance is it? You're going to have to do that. Okay? Okay, let's look at question number 2. This is more like, this is what we're going to be doing in lab, where it's a reaction instead of just a hot thing cooling down. But we can still figure out the delta H, which is the same as, anyway, this is the same math. All right, so, yeah. Oh, I skipped it, but was energy conserved in the process? It was, and it's because of this piece right here. We did not lose any energy. It was just transferred from the copper to the water. Because the law of conservation of mass and the law of conservation of energy are essentially the same words. So we are conserving. We are not, conserve just means that we're not like randomly losing things. Yeah. It's always going to be yes, even if it doesn't look like it's yes. Which is, it's a law of the universe. We're not creating or destroying energy. If it looks like it disappeared, then it's gone somewhere that you have not been able to account for it. In this case, I'm accounting for it, so it's definitely been conserved. Okay. So here, I have a 100 milliliter sample of 0.76 molar hydrochloric acid at 23 degrees, and I'm mixing it with a 100 milliliter sample of 0.76 molar NaOH at 23 degrees. The reaction that is occurring is a 1-to-1 reaction where the hydrogen off the HCl is interacting with the OH off of the NaOH and making water. This is what happens in any acid-base neutralization reaction. You've got H's and OHs that neutralize and become water. Okay? So the temperature of the solution increased and a max temperature of 28.2 degrees Celsius was recorded. I didn't type this. Recorded. Assume no heat was lost to the surroundings because it's insulated. The volumes were additive, and the specific heat capacity of the solution was 4.184. The density of the solution was 1 gram per milliliter. So this is just saying we have the same specific heat as regular water. And also, whoever asked it was one of you two. Don't remember. One of y'all asked me about Kelvin. Jordan asked me about Kelvin. See, Kelvin. It's the exact same thing. Doesn't change anything at all. And then the density of the solution is 1 gram equals 1 milliliter. Remember, I already said that. So this is telling us that our additive volumes, so 100 milliliters and 100 milliliters, that gives us 200 milliliters, which is 200 grams. That's the purpose of that density being in there, to let you know that you can substitute and have your mass. All right. So the question is, calculate the enthalpy change. This is the term that we use instead of Q when we're talking about reactions. So it's functionally the same thing. We're just calculating it because of a reaction rather than just a thermal heat exchange. Treat it just like Q. And we're going to talk about, not today apparently, we're going to talk about using or calculating enthalpy changes. You know what? No, this is going to be our last problem. We're going to make it quick, and then I got to get started on the other stuff. So, but anyway, treat it just like Q. And then this is the same thing. So I have 100 milliliters of HCl, which went from 23 degrees to 28.2 degrees. I know that 100 milliliters is 100 grams. I know that the specific heat is 4.184 or 4.18. I don't actually care if you round on that or not. And then I also have 100 milliliters of NaOH, which also went from 23 degrees to 28.2 degrees because I mixed them. This is what you're going to be doing in lab. We're going to have NaOH and HCl. You're going to mix them and watch the temperature change because it will. Because it's 100 milliliters, I know it's 100 grams. And again, 4.184 is my specific heat for that. So what I'm going to do is I'm going to calculate the heat of my solution. So what's actually happening, so up here, up at the previous question, we had copper and water. Here we have a reaction, which is this. Oh, come on. Which is this. And the water that it is happening in. So the reaction releases heat. The water absorbs that heat. Just like the copper got dropped in and released heat and the water absorbed that heat. Same thing, except I'm talking about the reaction that's losing the heat. So my solution changes temperature. I'm going to treat it just like Q. I have 200 grams of solution. I was told 4.184 joules per gram Kelvin, but it's degrees Celsius, whatever. Like I said, it's the exact same thing. And I know that my temperature change, I went from 23 degrees to 28.2, so 5.2 degrees. And I'm going to write Kelvin because Kelvin, but so Q for my solution is that. Who had a question? Who said it? Yeah. No, wait. What? Final temperature minus initial temperature. Yep. So my solution, and I'm going to round it, gained 4,400 rounded joules of energy. Where did that energy come from? Because remember, we're reaching thermal equilibrium. In this case, I didn't add a hot piece of metal. I did what? Anybody? I said, so the solution gained 4,400 joules of energy. Where did it come from? So I'm going to do what I did again. Where did it come from? Yeah, the reaction. So I can't go put a thermometer on those little H pluses and go, how much temperature are you changing? I can't do that, right? But what I can do is measure the change in the solution that the reaction is happening in. And based on how calorimetry works, I know that those two amounts are equal. So equals the heat of the reaction. So the reaction loses 4,400 joules of energy, which is where the solution gets the 4,400 joules to gain temperature. Does that make sense? And then you would calculate the heat per mole. I'm not going to do that because I'm not going to ask you that. Not even in, I think we would do that in lab. B we're going to skip. No, sorry. A, we're actually not going to fully calculate it. But this is what we're going to be doing. We have a reaction happening in a solution. If we can calculate this for the solution, we know it is equal to the amount lost by the reaction that's occurring in the solution. Okay, B, endothermic or exothermic. Anytime that, okay, hold on. Our solution got hotter, right? Which means that we added heat to it. Yes? Right? Okay. In order for that to be true, what must have happened to my reaction? My reaction didn't gain heat. My solution did. My reaction lost heat, which makes it exothermic. Yeah, the solution gained heat because the reaction was losing that heat. When you mix an acid and a base, it is an exothermic process. It is an exothermic reaction, and it will release heat. So, no. For an acid-base reaction, yes, but not always true. There are some reactions where they lose heat. Like, all right, y'all are athletes, or at least interested in being sports medicine people. So you may not be athletes, but you've seen the ice packs that the trainers carry around that are room temperature, and then they go, and now it's cold, right? That is an endothermic reaction. So the solution that it is in is losing energy to the reaction. So that would be a situation where the solution isn't gaining the heat. Yeah. Energy is always conserved. Always conserved. And we prove that, well, we're not proving it, but we can only make this assumption that those two numbers are equal because energy is always conserved. If it looks like it's not conserved, then you have not accounted for something. So like I was saying, if I did this reaction in a glass cup, it's going to look like energy was not conserved. In reality, I just lost some of the heat to the glass and to the exterior, and it wasn't all in the solution. So it just means you haven't accounted for something if it looks like you haven't. Okay, I'm going to give you one more thing, and we're going to talk about it, and we will continue. How many of you guys watched the video about 3 different ways to do the thermochemistry calculations? It was one of the 4 videos I said to watch in more class today. Nobody? Okay, so this question that we were just working on is a good lead-in to what we're going to be talking about, the thermodynamics of chemistry. So when I'm talking about the amount of energy that a reaction does, so what we would have eventually gotten to our the answer to A is talking about the amount of heat energy per mole associated with the reaction that we are looking at. And there are multiple ways that we can actually calculate this, and it's going to be a little bit different for each way that we calculate it. So we are going to look at the 3 different ways that we can calculate the energy involved in a reaction. So this first one is using the enthalpy of formation. So enthalpy, again, is just like Q, but it's when we're talking about a reaction as opposed to just thermal exchange. All right? So this first one, we are looking at the heat of formation. So scientists have in a lab over time figured out how much energy is associated with the formation of various compounds. You're going to need your reference packet out for this. There is a table here that has a whole bunch of standard enthalpy of formation values. Right? And so there's also on the front of your reference packet a formula. Where the heat of your reaction is equal to the sum of all of your heats of formation for your products minus the sum of the heat of formations for your reactants. All right, so we are going to go to this table that I just pointed out to you, and we are going to find the standard enthalpy of formation or standard heat of formation for all of these compounds. Pay close attention to the state function, which is the G or the L, as you're pulling these numbers. So C2H6 is in the left-hand column. This, that guy is negative 84.68, and it's kilojoules per mole is the unit. All right, oxygen gas is 0 because that is its standard state. CO2 gas is in the left-hand column, negative 393.5 kilojoules per mole. And then liquid water is in the right-hand column, and it is negative 285.8. Does everybody see? I know it's in alphabetical order by name of element, but does everybody see, at least, has everybody found the table where the reference values are? This is the amount of energy it takes to form that thing from its component elements at 298 Kelvin. That's what a standard enthalpy of formation is. So in order to, once you have those values, and again, you're given these, and you're also given that formula, if it takes negative 393.5 to form a carbon dioxide, in this case, I'm forming 2 carbon dioxides. So I would multiply by 2. But you're just adding, I'm breaking these guys apart and putting these guys together. And that's what that formula does for us. So down here in the formula, the Greek letter sigma just means sum, and N is just your coefficient from the balanced equation. So I'm going to add up all of my products. So I've got negative 393.5 times 2 and negative 285.8 times 3. So those are my products. Minus, and then I'm going to do the same thing for my reactants. Negative 84.68 times 1, because there's no number in front, plus 0 times 3.5. And that tells you for this whole reaction where you are breaking apart these molecules and putting those molecules together, it'll tell you how much energy that takes. If it's a positive number, that means it's endothermic. I'm overall going to have to put energy in. If it is negative, that means that is an exothermic reaction, which means it will be releasing energy to its environment. And like I said, we are definitely going to be coming back to this on Tuesday. And again, remember I said it was kilojoules per mole. So, we're out of time for today. Please, so first of all, time out, your test on Unit 2 is next Thursday. So we will go over the 3 ways that we can figure out the amount of energy associated with a reaction. We'll go over those 3 ways. Please, for the love of God, watch the video that I told you to watch already, because then you'll have an idea of what's coming and we can move through, because I'm not going to be able to spend a lot of time on each. So watch that video. And even if you don't watch all of the other videos that I told you to watch, you are responsible for that information on the exam, so you'll need to watch it by then. If you haven't signed up for the extra credit opportunity and you want to volunteer on Saturday, please sign up. Go back to that email that I sent out. There's links. I need as many volunteers as possible because I'm going to have to rearrange my current volunteers as it is because I don't have enough. And that's it. That's all I got for you today.